Lesson 5.4 covers present value annuities. The present value of an annuity is the sum of all the present values of the payments. To better understand the purpose, let's look at an example. Suppose you want to withdraw $25,000 each year for the next 4 years. You must set up an account with enough money in it to be able to make these withdrawals. So suppose you have a child going to college and you want that child to have $25,000 each year to use during that year of college for the next 4 years. And you want to set up an account now in order to be able to do that. Well, if we look at it straightforward without interest, if we multiply the 4 times the 25,000, we would need $100,000 in the account. But the way this works, when you deposit the money into the account, it's going to gain interest, or it's going to grow interest over those 4 years. So you're actually going to end up having to deposit a little less than $100,000 in order to make these yearly withdrawals. So we want to figure out exactly how much we want to deposit so that the initial deposit plus the amount of interest we get would allow us to withdraw the $25,000 each year. Well, this is the present value of the annuity. It's the present amount, the amount right now that I need in the account in order to make future withdrawals. The formula for this is V equals P times 1 minus, and then in a parenthesis, 1 plus R over N raised to the negative NT power divided by R over N. This formula is similar in some ways to the future value of an annuity, but it does have some differences. So let's look at those differences. First, instead of an A equals P, I have V equals P. Where A was our future value of the annuity, the V is the present value of the annuity. P is still the payments or the withdrawals that are made. R is still the interest rate. T is still the time, always in years. And N is still the number of times the account is compounded per year. And as we mentioned, this is the formula used to find the present value of an annuity. As an example, this account could be an account you are setting up now from which you want to withdraw money in the future, and that was the example that I gave a moment ago. Well, it could also represent an amount of money you are borrowing now, and you're going to make payments on over a certain number of years to pay off that loan. Well, let's compare the two formulas for the two types of an annuity. In the previous lesson, we looked at the future value of an annuity, and that future amount was A. Now we're going to look at the present value of an annuity. So we have the two formulas, and for any future value, the variable that you're going to use is an A. For any present value, the variable you're going to use is a V. So that's the easiest way to distinguish between these two formulas. Well, let's look at when to use each formula. You use the future value formula, the A equals P formula, when you're dealing with an amount of money that will be in the account at a future date. This time I'm adding to the account for a certain number of years to be able to get a certain amount in the future. With the present value annuity, I'm dealing with an amount of money in an account right now. And I'm going to take that money and I'm going to withdraw from it over a certain number of years. So if it's an account that I'm building, that's a future value annuity. If it's an account that I have set up right now that I'm withdrawing from, that's a present value annuity. So just a few examples. Whenever we talk about retirement accounts that are building up, that's a future value annuity. If I have an IRA or any account that I make regular deposits to, that's a future value annuity. And some books deal with sinking funds. That would be another example of a future value annuity. With the present value annuities, retirement accounts that are fully set up that I'm withdrawing from each year. That's the present value. Another example, an account which I want to set up now so that I can withdraw money for a set period of time. And that would be the example I started this lesson off with. And then another example we're going to look at quite a bit are car and home loans, or any loan with a regular payment schedule. So basically, to determine the main difference, if it's an account that I'm building up to get a certain amount in the future, that's the future value annuity. If it's an account that I have right now that I'm making withdrawals from, or if it's a loan that I have right now that I'm paying off, then that's the present value annuity. So let's look at some examples. And this is the one that we started out with. I just have more details in it now. You want to withdraw $25,000 each year for the next 4 years. You set up an account that earns 7% annually. How much should you put into the account? Well, first we notice that it's a compounded account because it earns 7% annually. Even though I don't see the word compounded, since it earns 7% each year, that interest is being compounded. The next thing you need to decide is this an account that I'm building for the future, or is this an account I need set up right now that I'm going to be withdrawing from over the next couple of years? And this is an account that I want to set up right now that I'm going to be making withdrawals from over the next 4 years. So this is a present value annuity. So my formula is the V equals P times 1 minus 1 plus R over N raised to the negative NT divided by R over N. And as we mentioned, V was my present value of the annuity. That's what I'm looking for this time. I want to know how much do I need to put in that account right now. P is the amount of the withdrawals that I'm going to make. And this time I'm withdrawing the $25,000 each year. So my P is $25,000. R is my interest rate, which is 7%. And if I divide by 100, I get 0.07. N is the number of times compounded per year. It's compounded annually, so my N is 1. And then finally, time is my number of years. I'm doing this for 4 years, so T is 4. And as with the previous examples, I'm going to go ahead and multiply NT. When I do that, 1 times 4 gives me 4. Now I'm ready to plug these into my formula. So V equals P, which was 25,000, times 1 minus, and then in parentheses, 1 plus 0.07 divided by 1. Close your parenthesis, that's raised to the negative NT, so that's raised to the negative 4, and that's divided by 0.07. So this formula, it just involves a few more steps on the calculator than the other one. So just to walk you through it on paper, we're going to begin inside the parenthesis in the numerator of that fraction. We always begin with that parenthesis first. We're going to say 1 plus the 0.07 divided by 1. Then I'm going to raise that to the negative 4 power. Now the problem is I'm subtracting that value from 1. And I don't want to clear that decimal off my calculator screen to do this. So what I'm going to do on my calculator, I'm going to make that negative and then add 1 to it. Because 1 minus 7 is the same thing as a negative 7 plus 1. I get a negative 6 both times. If I have 1 minus 3, that's a negative 2. Well, if I said negative 3 plus 1, I would also get a negative 2. So instead of saying 1 minus that parenthesis, I'm basically going to make that parenthesis negative and add the positive 1 to it. That's the way I'm going to do this on my calculator to avoid clearing out my screen. Then I'm going to divide by the 0.07 divided by 1, and finally we're going to multiply by the 25,000. So we're going to begin inside that parenthesis. So 1 plus 0.07 divided by 1. So 1 plus 0.07 divided by 1. And that gives us 1.07. Then I raise that to the negative 4 power. So press your exponent key, and then type in a 4, and then your plus or minus button to make it negative, and then press equals. And that gives me 0.7628. Now I need to subtract this value from 1. So I'm going to make this value negative by hitting my plus or minus key, and we see that we've made it negative. And then I'm going to add 1 to that. And that gives me 0.2371. Now I'm going to divide this by the 0.07 divided by 1. And since 0.07 divided by 1 is just 0.07, you could divide this by 0.07. But for practice, I'm going to go ahead and do it with the parentheses. So divided by parenthesis 0.07 divided by 1, and close your parenthesis and hit equals. And I get 3.3872. Now leave that in your calculator and multiply by the 25,000. And that gives me 84,680.28141. So now let's look at what we did on the calculator, and I'm going to list the steps on paper. So as I go through this, you try this on your calculator and check yourself with the steps that I'm listing. So first we said 1 plus 0.07 divided by 1, and we got 1.07. And in the denominator, since I just had 0.07 divided by 1 on my screen, I just went ahead and wrote 0.07. Now I raised that to the negative 4 power, and that gave us 0.76. And all of these decimals from here on continue on, so I've just got the ... showing that. Now instead of saying 1 minus 0.76, because I don't want to round that number, hit your plus or minus key to make that 0.76 negative, and then add 1, and you get 0.23, and that number continues on in your calculator. Now leave that number in your calculator and divide by the 0.07, or you can open up a parenthesis and divide by the 0.07 divided by 1 and close your parenthesis. And when you do this, you got the 3.38, and that number continued on. Leave that in your calculator and multiply by the 25,000, and you get 84,680.2814. And that decimal continued on. Since this is money, round it to 2 decimal places, and we get 84,680.28. So that account would need to have $84,680.28 in it now in order to withdraw the $25,000 each year for the next 4 years. And as we mentioned before, if we took the $25,000 and multiplied it by 4, that would be $100,000. But I said since you're earning interest during each of those years, we wouldn't have to have the full $100,000 in the account because it's going to grow interest each year. So we see from this example, we only had to deposit the $84,680.28. Well, let's look at the next example. You want to withdraw $1,500 each month at retirement. You set up an account that earns 8.5% compounded monthly. If you plan to make the monthly withdrawals for 20 years, how much will you need to have in the retirement account? So the first thing when I'm looking at a problem, I have to decide, is it a compound interest account or simple interest? This one tells me I earn 8.5% compounded monthly, so it's a compound interest account. The next thing you have to decide is, am I making a single deposit or a single withdrawal, or am I doing this over and over? This is a retirement account in which I want to withdraw $1,500 every month. So this isn't the lesson 5.2 formulas. These are the more complicated formulas where I'm making the withdrawals or the payments over and over. Then next I need to decide, Is this value a future value or is it a present value? Well, with this problem, I'm at retirement age and I'm ready to withdraw the $1,500 each month. So I need to have that amount of money in my account right now. So this is a present value. It's not an account that I'm building. It's an account that I've got established right now that I'm going to start making withdrawals from. So this is my V equals P formula. V is the present value of the account, and that's what I'm looking for. P is the amount of the monthly withdrawals, and that's $1,500. R is my interest rate, which is 8.5%. If I divide that by 100, I get 0.085. N is the number of times compounded per year. It's compounded monthly, so N is 12. And time is my number of years, and I'm doing this for 20 years. And if I go ahead and multiply my NT, 12 times 20 is 240. So now I'm ready to plug these into my formula. So I get V equals P, which is 1,500, times 1 minus 1 plus my R, which is 0.085, over N, which is 12, raised to the negative NT, so raised to the negative 240th power. All that's divided by the 0.085 divided by 12. So let's look at this in our calculator. So we're going to begin with the inside parenthesis, and that was 1 plus 0.085 divided by 12, and hit equals. And that gives me 1.00708, and that decimal continues on. Then we raise that to the negative 240th power. So hit your exponent key, type in 240, and then your plus minus to make it negative, and hit equals. Now I need to subtract this from 1. So as we did in the previous example, I'm going to make this negative, and then I'm going to add 1. When I do that, I get 0.8162. Now I have to divide this by the 0.085 divided by 12. So divided by parenthesis, 0.085 divided by 12, and close your parenthesis, and then press equals to do the division. And this gives me 115.23, and that decimal continues on. And finally, I multiply this by the 1,500. And that gives me 172,846.2597, and that decimal continues on. So let's look at those steps on paper. When I typed the 1 plus 0.085 divided by 12, that gave me 1.007, and that decimal continued on. Then when I raised that to the negative 240th power, I got 0.1837. Now you subtract this from 1 by making it negative and then adding 1. And when you did that, you get 0.8162. Then divide that by the 0.085 divided by 12, and remember you have to put that one in a parenthesis. And when we did that, we got 115.23, and that decimal continued on. And then finally multiply that by the 1,500, and that gave us 172,846.2597. Since this is money, round it to 2 decimal places. So we get 172,846.26 So you would need $172,846.26 in the retirement account in order to make $1,500 monthly withdrawals for 20 years. Next, we're going to look at amortizations. So suppose we had a retirement fund of $200,000 and we want to withdraw a certain amount each year for the next 25 years. How do we find the amount to withdraw each year? Well, if we look at this formula, the V equals P times 1 minus 1 plus R over N to the negative NT divided by R over N, we know the present value V would be the $200,000. This time we're looking for the P. So just like in the previous lessons, it would be helpful to have a formula that had P equals, where I wouldn't have to divide by that parenthesis each time. And as we saw in the previous lessons, we can switch the V and the P as long as we raise that big bracket, that big parenthesis that's being multiplied by P to the negative 1 power. I'm not going to change the exponent of the NT. It's the very outside exponent that I'm changing the sign of. So our formula to solve for P is P equals V times 1 minus 1 plus R over N to the negative NT divided by R over N, and all of that is raised to the negative 1 power. Well, when we plug in the known values and solve for P, we're going to be finding the amount from the account that the bank pays us each year, or the amount that we can withdraw each year. This is one example of an amortization. Other examples that we're going to use this formula for are car loans, house loans, or any type of loan with a regular fixed payment. So the formula that we mentioned before, the variables remain the same. V is still the present value of the annuity, P is still the payments or the withdrawals that are being made, R is the interest rate, T is the time in years, and N is the number of times it's compounded per year. This formula is used when the payment is required for a present value annuity. If I'm looking for that payment amount, or if I'm looking for that withdrawal amount. If I don't want to know the amount in the account, the total amount, if I'm given that amount and I'm looking for the payments. So this could be an account you are paying off, such as a car or a home loan, or it could be an account which the bank is sending you regular payments, such as a retirement fund. Let's look at an example. At age 65, you now have $200,000 in a retirement account that earns 6% monthly. You wish to make fixed monthly withdrawals for the next 25 years. How much will that amount be? So the first thing you have to decide when you're looking at these problems is that $200,000 an amount that you're saving up for in the future, or is it an amount that you have right now? Well, this time it says you now have $2,000, so that's a present value. And I'm looking for the withdrawal amount, so I want P equals V. That's the formula that I want to use. V is the present value of the account, and that's the $200,000. P is the amount that I'm withdrawing, and that's what I'm looking for. R is the interest rate, which is 6%. If I divide that by 100, I get 0.06. N is the number of times compounded per year, so N is 12 since it's earning this monthly. It's being compounded monthly. And T is my time in years. I'm going to withdraw from this account for 25 years, so my T is 25. And just like before, let's go ahead and multiply N times T, and 12 times 25 is 300. So if I plug these into the formula, I have P equals 200,000 times 1 minus, and then in a parenthesis, 1 plus 0.06 divided by 12, raised to the negative 300th power. All of that is divided by the 0.06 divided by 12. And all of that is being raised to the negative 1 power. So let's look at this in our calculator. When we type this into our calculator, we're going to follow order of operations. We're going to begin with the parenthesis in the numerator, and we're going to say 1 plus 0.06 divided by 12. Then we're going to do the exponent next. We're going to raise that to the negative 300th power. Then we're going to subtract that from 1. Next, we're going to divide by the 0.06 divided by 12. And then in this example, since that bracket has a -1 exponent, we're going to raise that to the -1 power, or use our reciprocal button on the calculator and take the reciprocal of it, and then multiply by the $200,000. So let's begin with the 1 plus 0.06 divided by 12. 1 plus 0.06 divided by 12, and that gives us 1.005. I'm going to raise that to the -300th power. So I hit my exponent key and I typed in 300, and then I hit my plus or minus key to make that negative, and then press equals. And that gives me 0.2239, and that continues on. Now I need to subtract this from 1, so I'm going to make it negative, and then I'm going to add 1, and that gives me 0.7760. Now I'm going to divide this by 0.06 divided by 12. So divided by parenthesis 0.06 divided by 12, and close your parenthesis, and then press equals to do the division. So that gives me 155.2068, and that decimal continues on. Now I need to raise this to the -1 power. You can do that with your exponent key, or if you remember, the shortcut to raising something to the -1 power is to press the 1 over x button. When I press that, I get 0.00644. Now leave that in your calculator and multiply that by the 200,000. And this gives me 1,288.602803. So just to write a few of these steps on paper, first we said 1 plus 0.06 divided by 12, and that gave us 1.005. Now since that came out to an even decimal, I know the 0.06 divided by 12 was the 0.005, and that's what I've typed on my computer screen. If you want to go ahead and do that, since that decimal terminated, you can, or you could leave it the 0.06 divided by 12. Then we raised that to the -300th power, and we did that on the calculator. You should get 0.22, and then that decimal continues on. Now you make that negative and add the 1, and that gives you 0.77, and that decimal continued on. Now either divide by 0.005 or divide by, open a parenthesis, type in 0.06 divided by 12 and close your parenthesis, and hit equals, and you get the 155.206. Now raise that to the -1 power, or press your reciprocal key, and you get the 0.0064. Multiply this by the 200,000, and you get the 1,288.6028. And since this is money, round that to 2 decimal places, so you get $1,288.60. So our monthly withdrawals from that account would be $1,288.60. So if you're at age 65 and you've got $200,000 in your retirement account, if it's earning the 6%, you would be able to withdraw the $1,288.60 each month for 25 years. In the next example, at age 62, you now have $550,000 in a retirement account that earns 5.5% monthly. You wish to make fixed monthly withdrawals for the next 30 years. How much will that withdrawal amount be? So the first thing you decide is the $550,000 a current amount or an amount we're saving for in the future? And this time it's an amount that we have right now, so it's a present value annuity. I'm looking for the payment amount, so I'm going to use the P equals V formula. My V is the current amount of the account, so that's the $550,000. My P is the payment amount, or the amount of the monthly withdrawals, and that's what I'm looking for. R is my interest rate, which is 5.5%. If I divide this by 100, I get 0.055. N is the number of times it's compounded per year, and this is earning the 5.5% monthly, so N is 12. And I'm going to do these withdrawals for the next 30 years, so my time is 30. And just like before, go ahead and multiply your N times your T. 12 times 30 is 360. So let's plug these into our formula. And I get P equals 550,000 times 1 minus 1 plus 0.055 divided by 12 raised to the negative 360th power. All of that is divided by 0.055 divided by 12. And then all of that is raised to the negative 1 power. So let's look at this on our calculator. So as with the previous examples, begin with the parenthesis in the numerator. So I have 1 plus 0.055 divided by 12 and hit equals. Now if you notice, this was a repeating decimal, so this is one where I have to keep it a fraction in the denominator. I can't round that to a terminating decimal. So I end up with 1.045 and that decimal continues on. Now I raise this to the negative 360th power. So hit my exponent key, type in 360, and hit my plus minus key to make that negative, and press equals. And that gives me 0.192775, and that continues on. Now I need to subtract this from 1, so I'm going to make it negative by hitting my plus or minus key, and then add 1 to it. So I get 0.8072. Next, I divide this by 0.55 divided by 12. So I have to say divided by parenthesis 0.055 divided by 12. Close your parenthesis, and then be sure to always hit equals to actually do the division. So that gives me 176.1217, and that continues on. Now I raise this to the negative 1 power. I'm going to use my reciprocal key, and that gives me 0.00567. And then finally, we're going to multiply this by 550,000. So that gives me 3,122.839508. So if we look at this on paper, when we said the 1 plus 0.055 divided by 12, we got 1.004, and that decimal continued on. And as I mentioned, since that decimal did not terminate, I can't change this fraction to a decimal. I'm going to have to divide by that fraction. So next, leave that 1.004 in your calculator and raise it to the negative 360th power. And when we did that, we got 0.19, and that decimal continued on. Now I need to subtract that from 1, so make the 0.19 negative by hitting your plus minus key, and then add 1, and you get 0.80, and that continued on. Then we divided that by 0.055 divided by 12, and remember you have to put that in parentheses. And when we did that, that gave us 176.12. Raise that to the negative 1 power, and I used my reciprocal key, and that gave me 0.005. And then finally, multiply that by 550,000, and you get 3,122.8395. And if we round this to 2 decimal places, I get 3,122.84. So this time I can withdraw $3,122.84 each month for those 30 years. Well, let's look at the next example. You contribute $2,000 per year to an IRA paying 6% annually for 20 years. How much will the account be worth at the end of the 20 years? Then the second part, when you retire, how much will you be able to withdraw per year for the next 25 years, assuming the interest rate does not change? With this question, you have to be careful. So let's take a closer look at this question. I'm being asked 2 different questions, but these questions are in 2 different times. In the first question, I'm asked how much will the account be worth at the end of 20 years? Well, this is a future amount, and then we're looking for the final value. So I'm contributing $2,000 each year, and I'm going to do this for the next 20 years. How much will I have in the future? So that's my A equals P formula. I'm looking for the final value, so I'm starting with A, and then it's the future value, the A formula, not the present value, not the V formula. So let's start with A equals P. My A is that future value that I'm looking for. My P is the amount that I'm depositing each year, so my P is $2,000. R is the interest rate, which is 6%. If I divide by 100, I get 0.06. N is the number of times compounded per year. Well, it earns the 6% annually, so my N is 1. And I'm going to do this for 20 years, so my time is 20. And just like before, let's go ahead and multiply the N times the T. 1 times 20 is 20. So if I plug these into the formula, I have 2,000 times 1 plus 0.06 divided by 1 raised to the 20th power minus 1 divided by 0.06 divided by 1. So since my N was a 1, I'm going to go ahead and drop those 1s before I do this in my calculator just to save a little this time. So the 0.06 divided by 1 gives me 0.06 each time. In the numerator, the 1 plus 0.06 divided by 1 would just give me 1.06. Now, if you left it the way it was and did it all on your calculator, that's fine. But this is what I'm going to type in my calculator. So I'm going to begin with the 1.06, and I'm going to raise that to the 20th power. And that gives me 3.207, and all of these decimals continue on. Then I'm going to subtract 1 to get 2.207. I'm going to divide that by 0.06, and that gives me 36.7855. And then multiply that by 2,000. And that gives me 73,571.1824, and that decimal continues on. So as we saw on the calculator, the 1.06 raised to the 20th was 3.207. Then when I subtracted the 1, I got 2.207. Then next I divided by the 0.06, and I got 36.78. And then leave that in your calculator and multiply by 2,000, and we got the 73,571.18. And if I rounded that to 2 decimal places, it would just give me the 0.18. So that means if I make those yearly deposits of $2,000 for the 20 years, my retirement account would have $73,571.18 in it. Now let's look at the second part, or the second question that we were asked. When I retire, how much will I be able to withdraw per year for the next 25 years? So that $73,000 that I just found is going to be the amount in my retirement account when I retire. Well, this time, at the time I retire, that's a present value. That's going to be the amount that I have right then that I'm going to start withdrawing from. And I'm looking for the amount that I can withdraw each year. So this time I'm starting with the P equals V formula. The 73,000, when I'm retiring, the time changes, so that becomes the amount that I have right now at retirement age. And I'm looking for the withdrawal amounts. So the V was the 73,571.18. The P is the amount that I'm looking for. We're going to assume the interest rate does not change. It stays 6%. So if I divide by 100, it's 0.06. The N is the number of times it's compounded per year, so it's annually, which is 1. And the T is my time in years. This time I'm going to make the withdrawals for 25 years, so my time is 25. So if I go ahead and multiply the N times T, I get 1 times 25 is 25. So plug these values into your calculator. So you get 73,571.18 times 1 minus 1 plus 0.06 divided by 1 raised to the negative 25th power. All of that's divided by 0.06 divided by 1. And then that bracket is raised to the negative 1 power. So just like with the previous examples, I'm going to go ahead and, to make the calculator part easier, divide the 0.06 by 1s. Now in my calculator, I'm going to raise 1.06 to the negative 25th. I'm going to subtract that from 1. I'm going to divide by the 0.06. I'm going to take that answer and raise it to the negative 1 power, and then multiply by the 73,000. So we're going to begin with the 1.06. I'm going to raise that to the negative 25th power. So hit your exponent key, type in 25, and then press your plus or minus to make it negative, and then press equals. And this gives me 0.2329. I need to subtract that from 1. So I'm going to hit my plus or minus key to make it negative. And then I'm going to add 1. And that gives me 0.767. Now I'm going to divide this by 0.06. And that gives me 12.78. Now I need to raise that to the negative 1 power. You can use your exponent key or you can use your reciprocal key. I'm going to use the reciprocal key, and I get 0.07822. And then finally multiply that by the 73,571.18. And when I do that, I get 5,755.231966. So as we saw in our calculator, the 1.06 raised to the negative 25th power was 0.232, and that decimal continued. If I make that negative and added the 1, I got 0.76, and that decimal continued on. Then divide by 0.06, and that gave me the 12.78. Raise that to the negative 1 power, and that gives me 0.078. And then multiply that by the 73,000, and that gave me the 5,755.2319. Round this to 2 decimal places, and that gave me 5,755.23. So our yearly withdrawals will be $5,755.23. Let's look at the next example. A couple takes out a mortgage for $250,000. If the loan is a 30-year loan compounded monthly at 9%, calculate the monthly payments, and then find out how much money did the couple end up paying for the home. So let's first look at finding the monthly payments. It's a compound interest account, so I know I'm not going to use the simple interest formulas. I'm going to be making monthly payments, so this isn't the lesson 5.2 formula. These are the larger formulas where I'm making repeated payments or repeated deposits. Then I ask myself, is this a future value or a present value? The $250,000 is a present value. That's something that I currently owe to the bank. So it's not a value that I'm building up for the future. It's something that I owe right now. So I know these are the formulas with the V in them. So since I'm looking for the payment amount, I'm going to use the P equals V formula. V is the current value that I owe on the home, which is $250,000. P represents my monthly payments, which is what I'm looking for. R is my interest rate, which is 9%. If I divide that by 100, I get 0.09. N is the number of times the account is compounded, and this one's compounded monthly, so it's 12. T is my time in years, and I'm taking out a 30-year loan. And if I go ahead and multiply the N times the T, 12 times 30 is 360. So let's plug these into our formula. I get P equals 250,000 times 1 minus 1 plus 0.09 divided by 12 raised to the negative 360th power. All of that's divided by 0.09 divided by 12. And then I raise all of that to the negative 1 power. So let's look at this on our calculator. So if we begin with the inside parenthesis, I have 1 plus 0.09 divided by 12. So 1 plus 0.09 divided by 12 and hit equals. And this gives me 1.0075. I raise that to the negative 360th power. So press your exponent key, type in 360, and then the plus or minus to make it negative, and hit equals. And this gives me 0.067, and that decimal continues on. Now I need to subtract that from 1. So hit your plus or minus to make it negative, and then add 1. And that gives me 0.932. Now divide this by 0.09 divided by 12. So divided by parenthesis 0.09 divided by 12 and close your parenthesis and press equals. And that gives me 124.2818. Now I need to raise that to the negative 1 power. So I'm going to press my reciprocal button, and that gives me 0.0080. And then finally multiply that by 250,000. And that gives me 2011.5565. So if we look at this on paper, the 1 plus 0.09 divided by 12 gave me 1.0075. Now to save room on my computer screen, when I noticed that that decimal terminated, I went ahead and took the 0.09 divided by 12 in the denominator and made it 0.0075. You can either do that, or you can do like I did on my calculator and just leave it the fraction. However you want to work this would be fine. When I raised the 1.0075 to the negative 360th power, I got 0.0678. Then make that negative and add 1, and you get 0.9321. Divide that by the 0.0075 or the 0.09 divided by 12, and you get 124.2818. Now raise that to the negative 1 power, and you got 0.008. And all of these decimals continue on. Don't clear out your calculator screen. Just write down the first few digits on paper. Leave that in your calculator and multiply by 250,000, and you got 2011.556. Now since this is money, round it to 2 decimal places, so we got $2,011.56. So the couple's monthly payments would be $2,011.56. Then this question asked, how much did the couple actually pay for the house? They paid $2,011.56 each month for 30 years. So I'm going to take the 2011.56 and actually use that rounded value because that's the actual amount they pay each month. I'm multiplying that by 12 because there's 12 months each year, and I'm multiplying that by 30 because they're doing this for 30 years. And this ends up giving me 724,161.6. So since this is money, be sure to put a 0 after the 6. So the couple ends up actually paying $724,161.60 for the home. Let's look at the next example. You take out a car loan for $15,000. If the loan is a 3-year loan compounded monthly at 8.5%, calculate the monthly payments. How much did you end up paying for the car? So this time I'm looking for the monthly payments, so I'm going to use the formula P equals V times 1 minus 1 plus R over N raised to the negative NT divided by R over N, and all of that's raised to the negative 1. So V is the amount of the loan, which is $15,000. P represents my monthly payments, which is what I'm looking for. R is my interest rate, which is 8.5%. If I divide by 100, I get 0.085. N is the number of times compounded per year. It's compounded monthly, so that's 12 times per year. T is the number of years. I'm doing this for 3 years. And then finally, I go ahead and multiply my N times my T. 12 times 3 is 36. So if I plug these into the formula, I get P equals 15,000 times 1 minus 1 plus 0.085 divided by 12 raised to the negative 36 power divided by 0.085 divided by 12, and all of that's raised to the negative 1. So begin with the parentheses. I have 1 plus 0.085 divided by 12. And that gives me 1.00708. And that decimal continues on. Now I need to raise that to the negative 36 power. So press your exponent key, type in 36, and then the plus or minus key to make it negative. And this gives me 0.7756. Now I need to subtract that from 1. So hit your plus or minus key to make that negative and add 1. And that gives me 0.2243. Now I need to divide that by, open a parenthesis, 0.085 divided by 12, and close your parenthesis, and press equals. And that gives me 31.678. Now I need to raise that to the negative 1 power, so I'm going to use my reciprocal key, and that gives me 0.0315. And then finally, multiply that by the 15,000. And that gives me 473.5130. So looking at this on paper, the 1 plus 0.085 divided by 12 gave me 1.007. When I raised that to the negative 36 power, I got 0.7756. Then I made that negative and added 1, and I got 0.2243. Then I divided that by, and you have to put this in a parenthesis, the 0.085 divided by 12, and that gave me 31.678. Then raise that 31.678 to the negative 1 power, and we got 0.0315. And then finally multiply that by 15,000, and we got 473.513. All of these decimals continued on, so you just leave them in your calculator. Don't ever round until the final step. Now this is our final step, so it's money, and we're going to round to 2 decimal places. So I get $473.51. So your monthly car payments are going to be $473.51. Then the second part of this question said, how much did you end up paying for the car? Well, you pay $473.51 each month for 3 years. So I'm going to take the 473.51 and multiply it by 12 because you're making that payment 12 times a year, and then multiply that by 3 because you're doing this for 3 years. When you do that, you get $17,046.36. So you actually end up paying $17,046.36 for the car.